Sheldon, Dan, do you guys want to be co-host too?
No, only if you think you need help or might need help. I'm just happy to be back.
Exactly. Yes. Hello.
I'll start in about a minute. Is that okay with you?
Oh, sure.
Okay.
Yeah.
Actually, it might be time. I think it just turned 3 o'clock.
Mm-hmm.
So welcome everybody to the first talk of 2023 in the Western Hemisphere Colloquium on Geometry and Physics. We are delighted to have Xin Sun of the University of Pennsylvania, and he will talk about random surfaces, planar lattice model, and conformal field theory.
Thank you very much for the invitation to this very interesting seminar. Today, I will talk about probability theory, which is related to conformal field theory. Conformal field theory, by definition, is the quantum field theory with conformal symmetries. And 2D conformal field theory in physics is motivated by the study of random surface and 2D lattice models. And it has influenced various branches of mathematics since 1980s, in particular, vertex operator algebra, quantum group, and geometry of moduli space. And in the last 2 decades, 2D conformal field theory has started to have a major impact in probability theory, especially on those related to random surface and lattice models. So my goal today is to give a sample of results and open questions in probability that is inspired by this movement. And so I should say that this sample is only a personal collection. And also I want to make it clear that my lecture is not a lecture about conformal field theory by itself, but my hope is that after this lecture, you will be more motivated to learn yourself. Yeah. Okay, so I will start by discussing the story for random surface. And before I go to random surface, let me first recall the more classical story for random path. So in probability, there are 2 ways of sampling. There are two type of ways of sampling a canonical random path. One is to use the so-called scaling limit of a discrete object, and in this case, it's a scaling limit of a simple random walk. And the other method is to completely using the continuum. So here, this graph is a sample of a simple random walk, conditioning on starting and ending at the origin, and you run for a certain time, and then you do a scaling limit. So in the scaling limit, it will converge to something called the Brownian motion. And in this case, since I assume that the starting and ending point are at the origin, this will be called the Brownian bridge. And this result is called the central limit theorem. And so there's another way computing the continuum to construct the Brownian bridge, which is simply we consider this random Fourier series. And here, so this is a normalized Fourier mode. And this alpha n are just IID Gaussian random variables. And you can show that this random Fourier series, it converges almost surely in this uniform topology, which defines a random function on the interval 0, 1. And this is also, and this random function is a Brownian bridge. So, so to sum up, so in order to sample a canonical random path, we can either do a scaling limit of a natural discrete object, or we can directly construct it from the continuum. Okay. And the similar story has been carried out in the last decade to a random surface. And so here is the scaling limit of this uniform of this discrete approach. And here we want to consider. So we want to sample a canonical random surface from the uniform measure. And since there are infinitely many surfaces, we need to do a discretization. And the way to do it is we first fix the size n, and we consider all the, we uniformly sample a triangulation of the size n. So here the size could mean the number of triangles in this surface. And then we view this as a piecewise linear Riemannian manifold. Okay, and so in the space of compact metric measure space, there's a natural topology called the Gromov-Hausdorff-Prokhoff topology. And it has been shown in these two landmark papers that this random Riemannian manifold, after proper scaling, it converges to a random metric measure space in this natural topology. And this limiting object is a random metric measure space. And it can be shown that this metric measure space, the topology is almost surely a sphere. And this limiting random sphere is now known as a Brownian sphere. This is the direct analog of the Brownian bridge in the one-dimensional case. Okay. So in the context of two-dimensional quantum gravity, this problem of sampling a random surface was also considered from a different point of view, namely from this conformal geometry point of view. So here by quantum gravity, I just mean random geometry, because quantum, at least in my dictionary, it means random, and the gravity means geometry. So if you have quantum gravity on some topological surface, it just means I want to sample some random geometry given this surface topology. And so one way to approach geometry on surface is to from this conformal geometry point of view. So here there is this natural notion of conformal equivalence, which means that so suppose I have two Riemannian manifold, they are conformal equivalent if and only if there is a conformal map, which locally look like a scaling. And this scaling factor is a so-called conformal factor. And then, so suppose I have some random geometry on a topological surface, I can first conditioning on it being conformally equivalent to a fixed Riemannian manifold. And after that, this random geometry can be written in the following way, where I just need to understand this conformal factor, this random conformal factor. And this reduced the study of random geometry on surface to the study of random functions on fixed Riemannian manifold. And this is the point of view taken by Polyakov in his original paper in 1981 on the quantum geometry of bosonic string theory. So, in that paper, he argued that this conformal factor is governed by a quantum field theory with a Liouville action. And moreover, that quantum field theory have conformal symmetry, and this is a so-called Liouville conformal field theory. And right. And in the last 10 years, Polyakov's vision to quantum gravity has been made rigorous in probability. So his idea in modern probability language can be summarized as follows. If I consider a conformal embedding of a Brownian sphere, then it is described by the Liouville quantum gravity on the sphere with the parameter square root of a third. And the law of this conformal factor is governed by this Liouville CFT. So here, the so-called Liouville quantum gravity is a random geometry induced by variance of the so-called Gaussian free field. And this Liouville conformal field theory. Question?
Yes. What do you mean by the parameter, the square root of a third? Is that what people usually call Q or B?
Right. So this, so our parameter is gamma. Gamma equals to 2b, and this b plus b minus equal to q. This is the physics parameterization. But
okay. The a third is the gamma. The square root of a thirds is gamma.
Yeah. So the square root of a third is this gamma, and this corresponding to c equal to like 26, I think, where c is equal to 1 plus 6q squared.
Okay. Thank you.
Yeah. And I will mention this later as well. Okay. So what I mean by this Liouville quantum gravity, it now has a solid foundation. It is a random geometry induced by what I call variance of Gaussian free field. And this Liouville conformal field theory, at least mathematically, it can be viewed as a particular way of producing variants of GFF. Okay. So in the next few slides, I will first give a very quick review of this mathematical construction of Liouville quantum gravity, and then some background on Liouville conformal field theory. Okay. Before I goes into the detail of this claim. Okay. So let me first recall the definition of Gaussian free field. So the Gaussian free field is a natural analog of Brownian motion and Brownian bridge, but parameterized by a surface. So suppose I have a Riemannian manifold, and so I still consider these Fourier modes, which are the non-constant eigenfunctions of the Laplacian operator, and I normalize in the following way, and then this Gaussian free field on this Riemannian manifold is just given by the Fourier sum of this, given by this random Fourier sum. And in contrast to the Brownian bridge case, in this case, the convergence doesn't hold in the continuous function topology. It only holds in some generalized function topology. In particular, it holds in subreal space with negative index. And moreover, if you consider the correlation function of the covariance, the leading order has a logarithmic singularity. It means that if you fix a point z, the value of the function at a single point is not well defined. However, what is well defined is that if you consider the average of this function over a circle, then this is a well-defined function. And this plot is plotting this regularized Gaussian free field. Okay, so as I mentioned, this Liouville quantum gravity is the random geometry induced by Gaussian free field. So here, let's suppose this phi is a variant of Gaussian free field. So here, what I mean by a variant of Gaussian free field, it means that this phi can be locally written as a Gaussian free field plus a more regular function. Okay, so whenever a function can be written in this way, I call this a variant of GFF. Okay, and all of the construction here works if you first imagine this phi is just a Gaussian free field, and then you realize that if you add in a regular term, the construction doesn't change. Okay, so for this slide, we can keep in mind that maybe this phi is just a GFF, but you can also add a regular perturbation. And so if we want to define the random geometry, we want to define the area and the metric quantities. So here, the random area in the Liouville quantum gravity is defined as follows. It formally can be written as e to the gamma phi, where this gamma is a coupling constant. And so, as I mentioned, this Gaussian free field is not a pointwise defined function. So in order to rigorously make sense of it, we need to first do a regularization, such as the following one. And then we need to have a normalization procedure. So, and there's a theory called Gaussian multiplicative calculus, basically saying that this limit exists if gamma is between 0 and 2. And this will be the parameter range that I will focus on during this lecture. And then in this range, this has a limit. So the limit will be a random measure on this underlying surface. And this is a so-called LQG area measure. And if our surface has a non-trivial boundary, the same Gaussian multiplicative calculus theory can be used to define a length measure. And so technically more difficult, but conceptually similar, we can also define a random metric by first regularizing this phi and then taking a limit. But since the metric is much harder than a measure, so this Gaussian multiplicative calculus theory doesn't work. So there's a much more difficult, so showing that this limit is well defined for a properly chosen exponent, this is a much more difficult question, but this has been recently addressed in these works. And to summarize, so given the instance of Gaussian free field or a variant of Gaussian free field, we can define this random area, random boundary length, and random metric. They together form a random geometry, which I will refer as gamma LQG. And as I mentioned, so this Liouville conformal field theory is a conformal field theory which is recently rigorously constructed by making sense of this defining path integral, and this is also based on the so-called Gaussian multiplicative calcs. And so what it mathematically what it does is it produces a variant of Gaussian free field on each remaining manifold. It was originally done on the sphere in this seminal paper, but later it is generalized to all the other surfaces. And this one on the annulus is the one I want to particularly highlight it, because later in my talk I will discuss this annulus case. But this has been done in any remaining surface. Okay.
So sorry, I'd like to ask another question if I may.
Okay.
So in the physical point of view, when you write the Liouville action, of course you write the Laplacian of phi squared plus the linear dilettante field, the Q phi.
Right. Yeah, there's also Q. Yeah, right.
But that's what you just answered my question. So you were including what physicists call the cosmological constant term.
Yeah. The cosmological is here. Yeah.
Yeah. So you're including that. Okay.
Right. So this cosmological constant is positive. Yeah. Right. So this is constructed, and if you so this Liouville action. So there's a Liouville potential, and the Liouville potential is basically the total mass of this area. Right. So once you can make sense of this area measure, the total mass is well defined. You just weight it by the total mass. This is how this Liouville field theory is defined. So the important thing about two-dimensional conformal field theory is that so two-dimensional CFT, they enjoy local conformal symmetry because of the Riemann mapping theorem, and the symmetry algebra is an infinite dimensional algebra called the Virasoro algebra, and this is a very rich algebra, and the implication is that this two-dimensional CFT, it is exactly solvable in many cases, including the Liouville. And in the Liouville case, the rigorous solution is recently achieved in these remarkable works. Okay. And so in this talk, I will not go into the detail of how this is defined rigorously, but just keep in mind that Liouville CFT is a rigorously defined quantum field theory that produces exactly solvable variants of Gaussian free field. And these variants will be related to random surface / quantum gravity.
Excuse me, can I repeat Greg's question?
Okay.
So I did not understand your answer. So phi for you is a Gaussian field, or is it the field whose dynamics is governed by the full Liouville action, including the cosmological constant?
So phi is so in the Liouville conformal field theory, phi is going to be governed by this Liouville action. And in probability, what you can do is you can first sample a free boson with a background charge Q, and that is like a free field with a background charge Q, and then you can add this Liouville perturbation by reweighting the measure by this total Liouville area. Yeah.
Okay. Well,
so it's not like you expand in mu. It's not like you expand in mu. You just condition your measure on requiring that the total area measured with respect to the Gaussian field is fixed to be equal to something. Yeah, exactly. Yeah, so you can just condition on this total area be equal to 1. And that has the same effect. So basically there are different variants. So one variance is that you can consider your surface has a free area, and then this area will be like a power law. And once you weight it by this total mass, you will gonna get a gamma function. That's one option. The other option is you can condition on this area to be 1, and then you get a normalized. Yeah, but in either cases, the field theory you are going to get is going to be non-Gaussian because of this reweighting conditioning. You said non-Gaussian.
It's a non-Gaussian, yeah.
But how do you deal with non-Gaussian theories in probability theory?
That's what has been achieved in these remarkable papers. Yeah. So usually it is not dealable, but it's happened to be people are able to do this. Yeah.
But this is a crucial point, and and I want to. I mean, I'm glad Nikita's following that up, because I mean, we absolutely cannot expand in mu. We know that because the answers from the matrix.
Yeah, we don't expand. Yeah. So the solution. So the proof of DUZD formula under the conformal bootstrap is not by expanding in mu, because it's not possible. If you just if you look at the correlation function, it's going to be new to a fractional power, and this is not really expandable.
Short analytic and mu.
Yeah, right.
But I'm puzzled how you're going to get that by using these Gaussian methods, these IID Gaussian distributions.
I mean, so this Gaussian measure is only to define these quantities. So once you have these measures, you can rigorously define the correlation function. But the way to prove that this correlation function satisfies DUZD formula, it requires like several papers. Yeah, it's like that's definitely not straightforward. So the idea of proving the DUZD formula is to first using this. The proof of DUZD formula is basically by implementing Teschner's idea. Yeah, so Teschner shows that the DUZD formula is a unique solution to some shift equation. And then, so he used a 4-point function and BPZ equation to derive these shift equations. And that is what these mathematicians were able to make sense of. Yeah, it doesn't directly use expansion in mu.
Yeah, but so, I mean, the conventional approach would be not to do expansion in mu, but to expand in phi around the classical solution and just do finite diagrams. Then phi would be a Gaussian in the first approximation, but massive field, most likely, for example.
Yeah, so that could, yeah, but so I guess my point is really like that this Gaussian multipliers, it provides a way of defining this correlation function rigorously. And since we know that DUZD formula is an explicit formula, at least we can formulate a conjecture saying that this correlation function equal to DUZD formula, right? But proving this conjecture is a very difficult task in mathematics, which is not something I would be able to explain in like 5 minutes. So,
but bottom line is that you can derive DOZZ from Gaussian ensemble.
Yeah. So the bottom line is DOZ formula can be derived by by just making sense of the Feynman path integral and the condition error to be 1, and then derive the correlation function. This can be derived. Yeah, and it has been achieved in this work. Yeah.
Thank you.
Yeah. Okay, so this is some discussion about Liouville theory, and now so let's coming back to this Polyakhov's idea. So Polyakov was saying that the conformal embedding, the conformal embedding of the Brownian sphere is given by this Liouville quantum gravity geometry induced on the Riemann sphere with this parameter gamma equal to the square root of a3rd. And moreover, this conformal, the law of this conformal factor is a variant of Gaussian free field, and this variant is produced by this Liouville CFT. Okay, so that's the, and if you want to have a more precise version, it means that first we can sample a phi, a random function phi on this Riemann sphere according to this recipe of Liouville conformal field theory, and then we can consider this matching measure space where this guy is an LQG area and this is an LQG metric, and then the claim is that this is going to be isomorphic to this Brownian sphere, which we constructed from the Gromov-Hausdorff limit of this uniform triangulation. And moreover, it should be the case that uniform triangulation under conformal embedding, it should converge to this limit. So this is the rigorous formulation of Polyakov's idea on bosonic string theory, at least in the pure gravity case. Okay, and this vision is very much realized due to over the last decade. So first of all, there is this theorem by Miller and Sheffield. So they show that, so Miller and Sheffield, they were able to construct an explicit variant of Gaussian free field without referring to CFT or any other theory. They were able to construct an explicit variant of GFF, and then they can define this random metric measure space. They can show that this guy, as a metric measure space, is isometric to the Brownian sphere. This is done by Miller and Sheffield in their fundamental work. And then, so I have a work with some other co-authors. We show that this Miller-Sheffield variant of Gaussian free field, it indeed agree with this Liouville CFT variant produced by making sense of the Liouville action. If you're putting these two together, we know that this is realized, at least. Okay. And there's also a similar story for the disk. The only addition is that in this case, you random metric measure space also have a length measure. Yeah, but other Otherwise, it will be the same. And the disk variant is also verified. Yeah. So, right. And about the last statement about the scaling limit. So here I only have this word should here because this is so far still a conjecture beyond one concrete example. So in my work with Holden, we show that this conjecture holds under a particular variant of conformal embedding. And in the next maybe 20 minutes, this will be, I will explain our theorem. Okay. So first of all, so what do I mean by a discrete variant of conformal embedding? So I will just give you one example to demonstrate this idea. So this is one very famous example of a discrete conformal embedding is called circle packing, and so there is a theorem by these people. They said that any triangulation, it can be uniquely modulo mobile transform to be embedded into this sphere where the vertex is the circles and the edge is the tangent relation between the circles. And then Thurston has this conjecture that circle packing provide a discrete approximation of Riemann mapping. And this is proved by Rudy and Sullivan. So basically, given any Jordan domain, you can approximate your Jordan domain into a triangular lattice, and you can represent the triangular lattice as these regular circle packings. And then using this circle packing theorem, you can map this thing into a circle packing of a unit disk with these irregular circles. And then Thurston's conjecture is that if you're shrinking the size of this circle on the left-hand side, this map will be approximating this Riemann mapping from this Jordan domain to the disk. And in this sense, circle packing is a discrete variant of conformal embedding. And the scaling limit conjecture that I referred to exactly says that under these type of embeddings, the uniform triangulation should converge to this random geometry on the unit disk, governed by this Liouville quantum gravity, whose conformal factor is sampled from Liouville CFT on the disk. So more precisely, so in this like a random, so in this disk, the measure is gonna be defined by the basically I will just assume that all the circles have equal mass, and this will give a random area measure on the unit disk, and I define the distance between two different circles to be the graph distance on this triangulation. This gives a random metric and random area. So yeah, then the conjecture is that as the size of triangulation tend to infinity, this random area random metric is converging to Liouville quantum gravity with gamma equal to square root of a third, where this variant of GFF is governed by Liouville CFT. The circle packing variant of this conjecture is still open. The only proved case of this conjecture is under another variant of another discrete conformal embedding, which is the so-called Cardis-Smirnov embedding. And this is the work I did with Holden 3 years ago. Yeah. Okay, so I think there might be a question in the chat. Okay, but it's already answered by someone else. Yeah. Okay. Okay, so next I will just explain our theorem. Okay. So this Cardis-Smirnov embedding, it is defined using a statistical mechanical model called the percolation. So here, the percolation just means the following. So suppose I have some lattice, maybe it is defined on a certain Jordan domain, and then a side percolation is just I sample IID color. So I use so I independently color every site black or white with probability P, and then once I color this, I also have these 4 mark point on the boundary, and then I can consider the event that this percolation has a white crossing. This means that there is a connected path which is colored white from this left boundary to the right boundary. Okay, so I can consider this event, and then so there's a famous theorem by Henry Kasten saying that if my probability of being white is bigger than 1/2, then this crossing probability will converge into 1 as the size of the lattice tend to 0. And if P is smaller than 1/2, this will tend to 0. And the P equal to 1/2 case is the so-called critical case. And in this case, he showed that this limit is non-trivial. Okay. And later, there are some more precise conjectures on this limit. So it is conjectured by Michael Eisenman that this thing should have a scaling limit, and this scaling limit should be conformally invariant. And namely, it means that this limit only depends on the cross ratio of the 4 points. And in 1992, Zhuang Cardi derived an exact limiting formula in a case where this Jordan domain is a rectangle, and it's based on conformal field theory. And Cardis formula and Eisenman's conjecture, they are both proved in this remarkable work of Stas Smirnov. So what he showed is basically by constructing a conformal embedding, which is now we call the Cardis-Smirnov embedding. So Smirnov's idea is the following. So he considered the unique conformal mapping from a Jordan domain with 3 mark points into this particular equilateral triangle. So by Riemann mapping theorem, such a Riemann mapping is well defined because I fix 3 boundary point. Okay, and then then he want to construct a discrete approximation of this Riemann mapping. So the way he did it is he considered this percolation model on this Jordan domain, and then maybe I'll draw a picture. So I have a Jordan domain with these 4 mark points, and then for every point inside the Jordan domain or on the boundary, so he defined 3 events. So this probability is the event that there is a white crossing that separate AZ and BC. So this is one event. And then he similarly defined the other 2 events, which is there is a white crossing separating BZ and AC and separating CZ and AB. So he defined these 3 numbers, and then he showed that these 3 numbers, it converged to this Riemann mapping. That's what he showed. And then if you, in particular, if you choose this point Z on the boundary, if you move this point Z to the boundary, this will exactly be the crossing probability. And then by Smirnov theorem, it's going to be equal to the evaluation of this Riemann mapping to this point D. And if you assume this Jordan domain is the rectangle, then by Christoph, I think it's called the Christoph theorem, you can write down the precise formula for this conformal map. That's exactly Cardis' formula. So this is Smirnov's proof of Cardis' formula. Okay. And similar to Rudin-Sullivan theorem for circle packing, Smirnov's theorem, it also provides a natural discrete conformal embedding, which is you simply compute these 3 separation probability for site percolation at criticality. And we call this embedding the Cardis-Smirnov embedding. And the result that I proved with Nina Holden is that under the Cardi embedding, this conjecture holds in the sense that if I consider a uniform triangulation on a disk with 3 boundary points, if I use this Cardis-Smirnov embedding to embed this triangulation into this equilateral triangle, then the induced random geometry on this equilateral triangle will converge to this square root of a third LQG, which is given by this. For example, this area measure is going to be given by e to the gamma phi dz squared, where this gamma equal to square root of a third. And this phi is going to be sampled from Liouville CFT. on the equilateral triangle. But once you know this on equilateral triangle, because this is a CFT, you can also map it to any other like surface. And this is based on joint work with many other co-authors. Okay, so this basically finished my discussion about random surface and its connection to conformal field theory. So here the important conformal field theory is this Liouville conformal field theory. Okay. Okay, so now I want to move to the discussion about 2D lattice model and the conformal field theory. So it is known in physics that many two-dimensional statistical physics models at their criticality, they enjoy conformal symmetry. For example, we have just seen the percolation case, but there are many more. And so in particular, there are three assertions. One is that the partition function of the model is going to behave as a determinantal Laplacian to a certain power. And this power is usually smaller than 1. And the correlation function is governed by a conformal field theory with a particular central charge. And this power here is exactly the central charge corresponding to the CFT. And the one example is percolation corresponding to C equal to 0. And this two-dimensional Ising model is another famous case, is corresponding to C equal to 1/2. So here, Ising model on 2D lattice is defined as follows. Its Hamiltonian is given by the summation of this like difference of spins. And then it is argued that there is a critical temperature, and at the critical temperature, the Ising partition function behaves as this 1/4 of the determinant inverse Laplacian, in some very precise sense. And because of this, the 2D Ising model corresponding to a CFT with a central charge 1/2 is a so-called minimal model with C equal to 1/2. Okay, so and this CFT point of view of two-dimensional lattice model is very powerful in the study of these models, but most of them were not very rigorous until the introduction of Schramm Loewner evolution. So basically, Schramm Loewner evolution is another approach introduced by mathematicians to study these lattice model at criticality. So the key observation is due to Schramm, which is so in these lattice models, there are many natural random interfaces. For example, if we consider a percolation, then if we color this left boundary black and the right boundary white, then there's a unique interface. Also, if you consider Ising model here, the domain walls are going to be these loops. This interface between plus and minus signs are going to be these collection loops. And what Schramm, he was able to argue that this random interface, they must be converging to a family of random curves, which is now known as SLE, indexed by a kappa. And this vision has been realized as many conjectures, and also there are a few results which are proven. The most famous case are due to Smirnov and others. So one is for the percolation case, this interface is going to converge to the SLE6. And in the Ising model case, these domain walls will converge to SLE3. And there is a precise formula between these this kappa value for this SLE parameter and the central charge of this conformal of this conformal field theory. Yeah. Right. Okay, so as I mentioned, Cardis formula for this crossing probability, it was derived by assuming that percolation corresponding to a CFT. And as I already mentioned, Ising model also corresponding to a CFT. So the difference is that the Ising model, it belongs to a family of very well understood CFT called minimal models due to this foundational work in CFT. But on the other hand, although percolation is believed to be described by CFT, it is something still quite mysterious. But without a full understanding of this CFT, Cardi was still able to make this important prediction just based on some generic principle about CFT. And the principle is that this crossing probability, it can be viewed as a certain 4-point correlation of a CFT. Moreover, the weight of this correlation function at these 4 different points, they are so-called degenerate weight. And it means that, so the mathematical meaning just means that this 4-point function is going to be the solution of a certain second-order differential equation, which is due to BPZ. So BPZ originally derived their equations in this context linear models, but their philosophy works for general CFT. And under this assumption, Cardi was able to derive his original formula, and which is in the form of a hypergeometric function. And if you know the definition of hypergeometric function, you know that this hypergeometric function is a solution to a certain second-order ODE. And that's exactly the BPZ equation in this case. So that's Cardi's way of deriving this Cardi formula. And Cardi's formula, so as I mentioned, this percolation can also be, the scaling limit of percolation can also be described by this SLE curves. Therefore, the Cardi formula can be viewed also as a formula about this SLE curve. And actually, from that point of view, you can also derive this Cardi formula, because this Cardi's percolation formula is just corresponding to the probability that SLE6 curve hit a certain boundary arc. And this is something can be understood using a method called martingale observable method. And using this method, you can derive many BPZ equation inspired formulas about SLE. And this is a very fruitful method to study SLE. Okay, so so the last result I want to present in this lecture is another formula for percolation, which is predicted by Cardi. It is also predicted using a CFT method, but it is not based on BPZ equation. And it's in my so to my knowledge, it's also hard to approximate approach using this martingale observable method. And this formula is just you still consider percolation crossing, but your underlying domain become annulus. So Cardi's conjecture is that if you consider an annulus, and then you consider the probability that there is a path connecting the 2 boundaries of the annulus, so he conjectured that the limiting probability is going to converge to a ratio of a bunch of delicate eta functions. And these delicate eta functions are are everywhere in CFT because these are the so-called Virasoro characters. And so this is Cardi's formula for this annulus crossing is not based on the BPZ equation. It is based on this another CFT related method called the Coulomb gas, and this is hard to assess using this traditional martingale method because if you want to introduce a martingale, you need to introduce a notion of time and a certain curve. But if you have annulus, there's no canonical starting point. If you want to do this, you need to first artificially choose a point and choose a curve, and then the problem becomes much more complicated. The analog of the BPZ equation in this case will become a second order PDE, which is like very hard to analyze. Okay. And the result I want to present is a joint work with my student, Zijie Zhuang and Shengjing Xu. So we prove that Cardi's formula for annulus indeed hold. And our proof is based on the CFT description of this quantum gravity on the annulus. So here, one interesting thing I want to emphasize is that this result is purely about the percolation on lattice, but our proof is based on quantum gravity annulus. So it's about the random lattice. Okay, so how much time do I have left, Ron?
About 16 minutes.
16 minutes, right?
But people were already asking you a number of questions. So if you need
Okay, sure. Maybe I will just wrap up in like 6 minutes, and then we can discuss more. Yeah. Okay, so in the remaining talk, I will first explain what is this CFT description of quantum annulus, and then I will briefly explain our proof. Okay, so in the beginning of the lecture, we have already seen that if we consider a Brownian sphere or Brownian disk, if you conformally embed it into a unit sphere or unit disk, then it will become this Liouville quantum gravity, where the conformal factor is sampled from Liouville CFT. So now let's do the same problem for the annulus case. So in the annulus case, what we can do is, so we can first fix these two annulus boundary length after some appropriate scaling, and then we consider all the annular quadrangulations with this boundary length. And now I sample according to this probability. So this gives me a Brownian annulus with a fixed boundary length, but random area. So, and this way of choosing this weight is called the Boltzmann sampling. So I can also like fix the number of vertices, but it will make my result a bit less clean. Okay. That's why I only fix these two boundary length, and I also fix this, and then I randomize my area. And without any surprise, this thing will converge in this natural topology of matching measure space. And we will define, and this will be called the Brownian annulus with boundary length A and B. And now we can play the same game. We want to conformally embed it into some cylinder, into a finite cylinder, and then we want to ask what is the law of this cylinder. So in contrast to the, in addition to this, in contrast to the sphere and disk case, in the annulus case, there's a new question, which is, we know that if you have two cylinders which have different modulus, they are not going to be conformally equivalent. Therefore, if we conformally embed our annulus into a cylinder, there is a law of the moduli. So this is a new question, and yeah. And the law of the modulus is also conjectured essentially in Polyakhov's paper, and also some follow-up works. So this is the conjectural law of this the moduli of the Brownian annulus that we proved last year with Morris and Remy. And the law also depends on this delicate eta function. And there's also another function which is related to this random variable. And this looks like a little bit mysterious, but this is equivalent to a conjecture in physics. So this is the conjectural description of this quantum gravity on the annulus, where the conjecture is that in order to sample this conformal factor, we need to first sample some random annulus. And then once we have this random annulus, then condition that annulus, I sample some Liouville field. Okay. And these normalizing factors, they are given by two CFTs. One CFT is called the bosonic ghost, and the other CFT is the Gaussian free field. And each CFT contributes a partition function. The product of these two partition functions give us this factor. Yeah. And this random variable, it comes because, so here I don't fix the boundary length. Okay. And here I'm fixing the boundary length. And this conditional boundary length give additional weighting. This additional weighting can be computed by solving the Liouville field theory. And this is given by this random variable. So this is what we proved last year. And by the way, this is a special case of a general conjecture for the CFT description of Brownian's surface with non-simultaneous connected topology. Okay. Okay, so I think maybe in the interest of time, I don't give the proof of the theorem because it's maybe a bit technical, but I will just say that we have a proof of this theorem, and the same idea of the proof of this theorem would also imply this percolation formula that I mentioned. So remember, the formula that I want to prove is that I have a crossing, so I want to compute the crossing formula for the percolation probability. And right, so
could you explain some notation? What's capital LF sub tau of d phi?
Oh, right. So this notation, this is a Liouville field on this cylinder tau. So we have a cylinder of modulus tau, and then we sample Liouville field on this. And the way to sample this.
And why is there an extra factor of the Gaussian free field?
Oh, right. So this is just the way I define this Liouville field is by maybe I can just I can explain the definition of this. So my definition of this Liouville field is so the definition of this is that I first consider a Gaussian free field. So I first consider a probability measure, which is the Gaussian free field. And then I add in this X, which is sampled from the big measure. So, and when I do this, this is same as the Gaussian free field in physics, except I didn't normalize. So I also normalized by the determinant Laplacian. So because I'm assuming that this p tau is a probability measure. So in physics, the Gaussian free field measure is usually something like this, where there's no normalization. But now I normalize by this partition function GFF, and this is going to be my LF tau.
Okay, thanks.
This is why, yeah.
Okay, it's clear. Yeah.
This is why I need to add it back, but this is only a conventional thing. Okay, so so I just want to explain at high level how this argument goes. So at the high level, what I want to do is I want to imagine my percolation is a so-called conformal matter on this random surface. So basically, I imagine that I have a Brownian annulus, and then I sample percolation, and then I conditioning on that this percolation have a crossing of the annulus, and this conditioning is like I introduce a non-trivial conformal factor with central charge C. This conformal factor, so I introduce a conformal matter with central charge C. This conformal matter still have central charge 0 because it's just a percolation condition on event. The central charge will still become will still be 0, and it means that this surface. So having this so introducing this conformal matter doesn't change the local geometry of my surface, but it changed the modulus. And the way it changed the modulus is determined by the partition function of this conformal matter. So what I did is I first compute the random modulus for this original Brownian annulus, and then after I reweight by this annulus crossing percolation, I can derive a new random modulus. And then by consider the Radon-Nikodym derivative between the two, it gives the partition function of the conformal matter. And in this case, by my definition, this partition function is exactly this annulus crossing probability. So by comparing the random modulus of the two surface of the two random surface, I can obtain the formula of this crossing probability. Yeah, and this is our philosophy. Okay, so this is basically all I want to say. Maybe I will wrap up my lecture by presenting you the general conjecture about the CFT description of pure quantum gravity, and I will stop there. By the way, so this idea of using quantum gravity to study lattice models is called KBZ relation, originally due to Kisnik-Pollack cosmological. But my understanding is that most of the KBZ argument is to predict scaling exponent, and our argument seems to be the first to derive a partition function. Okay, so this is the general conjecture about the CFT description of a Brownian surface. So here we are still going to sample a Liouville field on a Riemannian manifold with a certain conformal structure, and we are also going to have a random conformal structure. And this introduces a law on the moduli space. And this reweighting is also you need to use this partition function of this bosonic ghost. And there's also a natural measure on this moduli space. And in the case of torus, this thing also have explicit formula in terms of theta functions. And in the case of hyperbolic surface, this will be written in terms of Seiberg theta function and Weir-Peterson measures. And proving this conjecture, in my opinion, is one of the major open questions in Liouville quantum gravity. Yeah. And I will just stop here. Yeah. Thank you for your attention.
Well, thank you very much, Shane.
Thanks.
And let's take more questions.
Hi, can I just ask quickly what you mean by random triangulation or uniform triangulation in more detail?
Oh, yeah, right. So let me just, yeah.
Brownian sphere.
Okay, so that's the very beginning. Right, so uniform, so right, so basically a triangulation is just, for example, a triangulation of size 100 is, I have 100 triangles and I want to glue them together into a map, into a surface. And a particular such gluing is called a triangulation of the sphere. Let's say I'm gluing this into a topological sphere, and this is called a triangulation sphere of size 100. And if you fix the size, there's only finitely many ways of gluing them topologically differently. And if you uniformly choose one of them, it's called uniform triangulation. Yeah.
Thanks.
Tudor? You need to unmute yourself.
Can you hear me?
No, not really.
It's not very clear.
Give it a sec.
Okay.
Sorry, can you hear me now?
Yes,
Is
we
that
can.
any better?
Much better.
So sorry, I wanted to ask if there were any extensions of methods or approaches like this in higher dimensions, and how difficult do you expect that to be?
By higher dimension, you mean 3D gravity, or so?
Yeah, or I mean field theory and like conformal field theory and higher dimensions.
So I guess yeah. So one thing is that yeah, 2D. So here I'm mainly considered like 2D Liouville CFT, right? And I think if you consider if you allow some higher algebra, you can consider Toda theory. That's like that could be one like generalization. Toda CFT. And another generalization is this Liouville CFT is also supposed to related to like SL2R Chen-Simons and maybe WZW. This is like another generalization, I guess. But these are like still mathematically, they are still very mysterious. But some of the results we obtained in this direction, it also can be extended. Like some of the special cases can be extended, and there are certain predictions. But these are still poorly understood. Yeah.
Right.
Nejla?
Hello. Yeah, hello. Sorry, actually, I want to ask about another generalization of this 2D Liouville CFT for as the super Liouville CFT. This is something that
Okay.
personally I'm very interested in, and I think it's pretty much is well understood, and the super Brasser algebra is pretty well nice. So I feel maybe the starting point would be understand the relation of what you showed in one of the slides about the central element of Liouville and the parameter K or kappa, you called it. So yeah, so my concrete question is if we know about anything about that type of relation between central charge of super Liouville and any super version of those kappa or something like that.
Right. So this is a very good question, but so there's one fundamental difficulty in probability, which is in probability, we don't know how to deal with supersymmetry yet. It's like, so that's why we can only consider bosonic string theory. So bosonic string theory, there's only, this is essentially a probability measure, right? And if you have this supersymmetry, the partition function involve these like non-probability integrals. And as a probabilist, I don't know like how to make sense of those integrals. There were some, so in terms of supersymmetry, there are some hope, which is there are some connection between Liouville CFT and supersymmetric annulus. And so there are some concrete connection there, but that connection at this moment is only in terms of some formulas. So
yeah, but sorry to disturb, but that supersymmetry is not this supersymmetry. I mean the supersymmetry.
So you're saying like you're just saying like you have some like Z2 graded.
Exactly. So this one is already SUSY, and when we go from 2D Liouville to 2D super Liouville, what is happening for this SUSY is just become the orbifold of that. So that one, yeah.
I think, so I don't have a good answer to that question at the moment. I think, so I can imagine so first of all, so this probabilistic approach, this gave a lot of insight to this 2D Liouville CFT. For example, it can be used to justify like this, there's a fusion kernel formula by Ponson and Teschner, and this can be justified. So, and these kind of things, which are purely about Brasser algebra, but they are only justified recently using Liouville CFT. And I can imagine that these kind of like algebraic results, they might be able to help understanding this like super Liouville. But directly from probability, I think so far, at least I don't know any like random surface model whose conformal factor is this super Liouville. That I don't know. Yeah.
Okay, that was exactly my question. Thank you so much.
Okay, thanks.
Are there any other questions? Okay, well, the next talk is going to be by Thomas Grimm in 2 weeks. And let's all thank Xin for the beautiful talk.
Thank you very much for listening.
Thank you.
Yeah, thank you. See you.
Thank you.